Alright, section 4.6, Polynomial and Rational Inequalities. The main point behind this lesson is seeing the inequalities here with our polynomials and rational functions. In this case, you pretty much graph them the same way, you're just looking for different parts of the graph. Number one, when we solve this polynomial graphically, we do the same stuff. We look for the x-intercepts, and they occur at the value of -3, also at 1, and also at 4. As we take a look at each of those factors, notice how the x plus 3 is being squared, so now we know that this is a double root. We know that basically means it rebounds off -3. 1 is a single root, that way we know it just goes through, and 4 is also a single root, so we know that also goes through. Let's graph them. We have -3, 1, and 4. Another thing we know is that this polynomial has a leading term of x squared times x cubed times x, that's x to the 4th power. And we also see that it has a leading coefficient of 1. So 1x to the 4th, with this being positive and with this being even, we can see then that our end behavior is going from positive infinity to positive infinity. Okay, so as we graph this, since we know that -3 is a double root, it should rebound off -3, come up, it's going to work its way towards 1. Keep in mind that just because you see a y-axis here, that doesn't mean your graph should all of a sudden make that maximum occur at the y-axis and just go to that value of 1. Instead, it should be a more gradual process. Most likely, somewhere in the middle, right around here, you should see that there is a maximum there. So you rebound off, come up, and then you're going to go towards that next intercept at 1. As you go to 1, keep in mind what's going on here. It's a single root, so it's going to pass through 1, and then keep going, and then eventually also make its way down until you have to rebound to go back to 4. And then from there, 4 is also a single root, it passes through. And double check your end behavior. Are you going from infinity to infinity, basically? We are. It does look like a w, which is an x to the 4th polynomial, so everything checks out. We're all good. We're not done yet, though, because the problem is asking us to find when this polynomial is actually less than or equal to 0. So as we look at our number line, and even if we were to do sign analysis here, we have our intercepts at -3, 1, and 4. Those are our zeros, so I do want to say, because it's equal to 0, I can include those values. If you do sign analysis, just to save time, I won't do it, but the idea here is that what we're looking for is the section that is less than or equal to 0. Let's just do it for the part that actually does work. If I plug in a value like 2, let's say I test a value like 2, then I plug in 2 plus 3 squared is positive, times 2 minus 1 is positive, times 2 minus 4 is negative, and positive, positive, negative will give us a big negative area. Okay, so we should see that in between 1 and 4, we're getting the negative area, which is what we are trying to show here, that the polynomial is less than or equal to 0. And so part of our solution is going to say, well, you can include 1 because that's where it's equal to 0, and you go all the way until you reach 4. You can include 4 because that's also a 0. Anything in this region is going to give you negative numbers. Are there any other values that give you negatives? No negatives, because we'll see that this is positive, positive, positive. However, what we do see is that at -3 you do have a 0. So don't forget that you can actually have less than or equal to 0, so we want to include the value of -3 as well. And since it's just a solitary number, you just put that number in a brace. That's all. So that'll be your answer. It is a solution set of all values that exist for a polynomial that is less than or equal to 0. Okay, let's go on to the next page. All right, so in this next example, now we have a rational function. We're using the same technique. We're just trying to see where that rational function is greater than or equal to 2. So with a rational function, look for all your important things again: x-intercept, y-intercept, vertical asymptote, and horizontal asymptote. We have x-intercepts at x equals 4, so just 4 comma 0. And then the y-intercept, that's when x is 0, so that'll give us a let me do that as an ordered pair, as a y-intercept of 0 comma negative 2. The vertical asymptote occurs at negative 2 because of the denominator, and the horizontal asymptote occurs at y equals 1 since they are the same degree. All right, let's graph it. So we have y equals 1. We have a vertical asymptote at x equals negative 2. We have x-intercept at 4, 0, and also y-intercept at 0, negative 2. That right there, those 2 points can confirm you have your rational function in the quadrant, let's call it quadrant 4, and I'm kind of giving little air quotes here. Quadrant 4 of your quadrants. That looks like it's touching the asymptote. I want to make sure I never touch the asymptote. Okay, there we go. All right, and then now we need another section. Let's go ahead and test a value, let's say like at negative 4. If I test negative 4, I have negative 4 minus 4 over negative 4 plus 2. That'll give us a negative over a negative, so that'll give us a positive value. So I know that this area will not have any negative numbers, and therefore my graph is actually going to be in this upper left-hand corner, just like this. Okay. Now the question that this problem is asking us for is, when does this rational function, which we have already drawn now, when is this rational function greater than or equal to 2? Well, that's a y value. This is saying that the y value is 2. So when is this rational function basically a y value of 2 or more? And so we can see as we draw this, that rational function will actually at some point be less than 2. Everything in this area is definitely not what we want. We want our answer to be 2 and greater, which is going to be this section here. So we need to actually define what that is. The problem is now we're off the page. I don't exactly know where my function is actually equal to 2. So let's go ahead and solve this algebraically then. What we have is the equation x minus 4 over x plus 2. That's our rational function, and we're trying to find out when is this actually equal to 2. Let's find out what is the coordinates that actually make this true. So solving for this, let's actually solve for when x gives us a y value of 2. So we get x minus 4 equals 2 times x plus 2. That gives us 2x plus 4 equals x minus 4. That gives us x is equal to negative 8. So we'll get an x value of negative 8 and a y value of 2. That's when we actually see that the line intersects that horizontal line y equals 2. So therefore, what that's showing us is this shaded dark green area is all of the solutions that we want, which starts from negative 8. Can we include negative 8? Yes, we can. It's greater than or equal to 2. And we go from negative 8 all the way, well, we don't have anything in this territory, so all we want then is going up until we reach this vertical asymptote, which was at negative 2. Do we want negative 2? No, it's a horizontal asymptote. You can't include those values. So, did I say horizontal? I meant vertical asymptote. So therefore our answer, solution set, will be negative 8 to negative 2. Negative 2 non-inclusive. All right, going on to number 3. So again, we're still graphing, or rather solving polynomial inequalities. The last 2 examples we were graphing to really see our answer, but sometimes it doesn't make sense to graph. Let's just actually solve it algebraically. It just might be easier to solve algebraically. All right, so there's a little bit of a formatting error. Let's just go ahead and push this aside over here, and that way we can solve for, let's solve this as a right now, and that'll just kind of fall in line where it is. Okay, so we see here that we have x-intercepts at 1, at 3, and also at negative 5. And so what we do is we build our sign analysis chart. Since we're solving algebraically, we have negative 5, 1, and 3. Since the inequality says less than or equal to 0, you can include your zeros. I'm going to go ahead and give those solid dots saying we can have that as part of our solution. And then from here we can do our sign analysis. Since we have negative x plus 1, basically that is a line that is going down, will intersect at the value of 1. So I see the line with, since it's going down, I'll have positive values to negative values. So basically I'll have positive values until I reach 1, and then negative values anytime after that. And then we have the factor x minus 3. That is a line that is now have a positive slope, so it's going from negative numbers to positive numbers intersecting at 3. So I'll have negative numbers until I reach 3, and then it will be positive. And then we have our last factor, which is x plus 5, and just like x minus 3, it's a positive slope, negative until we reach negative 5, and positive anytime after that. So negative until we reach negative 5, and positive anytime after that. Let's see our end results. So we have positive times negative, that's positive. This gives us negative, this gives us positive, and this gives us negative. All right, so our final solution set, what do we see? We are trying to say, when is this polynomial greater than or equal to 0? Greater than means your numbers need to be positive, or equal to 0 means you can include your zeros. So as a final solution set, you can see we're starting off way over here, negative infinity, until we reach negative 5. Can we include negative 5? Sure thing, that's equal to. So include negative 5, union. We then start up again. We can include the value of 1, and we go until we reach the value of 3. These are all the positive values. You can include 3, and after that, there's nothing else. So that's going to be our answer right there. Negative infinity to negative 5, negative 5 inclusive, union 1 to 3, where 1 and 3 are also inclusive. Okay. So let's go ahead and go on to our, whoops, I just realized, I am so sorry, oh my gosh, this is not the right answer. I just realized that I was boxing greater than or equal to 0. It should have been less than or equal to 0. Oh my gosh. Okay, so that doesn't change too much. Obviously our sign analysis is still fine, but I just did the wrong area. So because it was less than or equal to 0, again, that formatting issue messed me up, so this is supposed to go over here. So less than or equal to 0 is going to be all our negatives then. So we want this area and this area. So let me just rewrite that answer. Now we're just going to say negative 5 inclusive to 1 inclusive, union 3 inclusive, 2, and then it's going off to infinity non-inclusive. Okay, so that's going to be your solution for letter A. Sorry about that. Hope that wasn't too much of an inconvenience. All right, let's go on to example B. I'm going to write this over here. So we have 2x minus 5 squared times x plus 2 times x minus 6 is greater than or equal to 0. So again, we are going to find the zeros. We have zeros at 5 halves, at negative 2, and also at 6. I'm going to go ahead and draw my sign analysis chart. I really should write smaller. I'm taking up so much space. So we have negative 2, 5 over 2, that's the same as 2.5. That'll come first. And then we also have 6. All right, let's do some sign analysis. So let's test. Do I want to test? No, let's just go ahead and do our factor method. I'm just going to erase this. Okay, so what do we have? 2x minus 5 squared. We have x plus 2, and we have x minus 6. So being a square, that just means that everything will be positive. X plus 2, it's a slope going up, so it'll be negative until we reach negative 2, and positive thereafter. And x minus 6, that's a line going up. That'll be negative until we reach 6, and then positive thereafter. What do we have now? We have positive, negative, negative, and positive. And oh, don't forget that I should have included this in the beginning. I apologize. We can have greater than or equal to 0. So I want to show that those are equal. And then now I can actually write my, oops, I can actually write my interval notation. I want this to be, let me just make sure I got this right, greater than or equal to 0. Greater than or equal to. So we want positives and positives. Or equal to. So that means this one too. So let's see what we got. Negative infinity to negative 2. Negative 2 inclusive. Union. We can have the value of 5 halves. Notice how it's in between two negatives. But 5 halves alone can be included. And then union. 6 being inclusive to infinity. And there we go. All right, do I have enough room for C? Let's see. Yeah, there's enough room. All right, so doing this, we need a factor. So let's take out the x squared. We get x squared. That's a difference of squares, so x minus 1 and x plus 1. Okay, so knowing that, we have zeros at 0, 1, and negative 1. Negative 1, 0, and 1. I have greater than or equal to, so I can include my zeros. Go ahead and give those closed circles. And then let's go ahead and do our process again. X squared, x minus 1, x plus 1. So since x squared is always positive, we'll have always positive everywhere. X minus 1, that's a slope going up. It'll go from negative to positive until we reach the value of 1. So negative, 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 positive. And then same thing for x plus 1, but this time negative until we reach negative 1, and then positive thereafter. Let's see what we get. This is a positive value. This is negative. This is negative. This is positive. So since we want greater than or equal to 0, we're going from negative infinity to negative 1 inclusive union. Oh, this is the same kind of situation. You can include 0. Union, go from 1 inclusive to infinity. And that'll be your solution for C. Where are we at right now? 17 minutes. Let's pause here. I'll go on to a part 2. Oh no, I did that again. Pause.